Oh, hey there. Let me tell you about the stacker crane problem. It's a decision problem that asks whether there's an efficient way to traverse a graph, making a number of required trips. We are given a graph containing undirected and directed edges. All of them are weighted, and we want to find a path that visits every directed edge and returns back to the start. Also, there's an upper bound on the length of the total path that we take. Formally, the problem can be expressed by defining the set stacker crane as a set of all GLB tuples, where G is a mixed graph, L is a function that assigns lengths to the edges, and B is the upper bound. A tuple is in the set only if there exists a cycle that traverses all the directed edges in G at least once, with total length less than or equal to B. The concept behind this problem is that the directed edges represent trips that we have to take. For example, picking something up somewhere and dropping it off somewhere else. And then the undirected edges are optional paths.
Let's examine the stacker crane problem with the concrete example of an area near Tufts. Say we're picking up packages from people who live on the one-way streets in this area. In this analogy, the area is our graph G, the one-way streets are directed edges, or edges in set A, two-ways are undirected edges in set E, street length is edge weight, street intersections are vertices, and we return to our starting vertex at the end to complete a tour. We know that we want to travel a distance of less than or equal to our given B, 57. We non-deterministically pick a street intersection to start at as our home base. We start off and end at our starting vertex. This cycle has a sum weight of 69, which is greater than B. Thus, we reject this cycle. Again, we start off and end at our starting vertex. This cycle has a sum weight of 57, which is equal to B, so we accept this tour. Distance-wise, we found the most efficient way to collect all the packages and return to home base.
We will do a reduction from traveling salesman problem to stacker crane problem. We will build a function f on input GW. The first step is creating new graph G prime. First, copy all the vertices in G to G prime. For each vertex vi in G, split into two vertices vi1 and vi2. Add a directed edge of weight 0 from vi1 to vi2. Then for each undirected edge vi, vj in the original graph, we make 4 undirected edges in the new graph: vi1, vj1, vi1, vj2, vi2, vj1, and vi2, vj2. Each of the new edge is weighted the same as the original edge. Then the second step is let L be a function that assigns weight to each edge in G prime as described in step 1. Lastly, our function outputs G prime LW. The tricky part for this reduction is we are transforming each vertex in traveling salesman problem to a directed edge in the stacker crane problem. Also, we made 4 undirected edge for the original undirected edge in the new graph. However, if we are moving from one directed edge to another directed edge, we are only using one of the undirected edges that we add. So if the weight of the cycle in traveling salesman problem is less than or equal to W, our new cycle in the new graph will still have a weight less than or equal to W.
We define the verifier V on GLBW. W is an ordered list of the vertices in G. First, we check if W is a cycle. If it's not, we reject. Then we check that all edges in the witness are also in A union E. If it's not, we reject the witness. The second step is that we check that all edges in A are also included in W. If not, we reject. Finally, we count the weight of W. We want to make sure that the weight is less than or equal to B, our upper bound. If it is less than or equal to B, we accept.
The stacker crane problem is difficult for a number of reasons. First, the solution requires us to visit every directed edge. This is a constraint on the tour we choose. Second, because of the upper bound on the solution's total weight, the stacker crane problem is about finding not just any cycle, but an efficient one. It's expressed as a decision problem, but by using lower and lower values of B, it can become an optimization problem where we need to find the optimal cycle that visits every direct edge. Finally, it requires finding a cycle in a graph. As the graph increases in size, it becomes exponentially more expensive to check every path, searching for a cycle. Because of all these reasons, there is no obvious way to solve the stacker crane problem for non-trivial graphs. Lots of current research has focused on finding different heuristics for approximate solutions.
Oh, hey there! Now that we know why a stacker crane problem is difficult, let's figure out why it's easy, shall we? So every stacker crane problem has a fixed cost, which is just the cost of all the directed edges. Now, there are plenty of undirected edges, which make the variables in this problem and give it more intricacy. The solution is, in theory, the cost of a fully directed graph would just be the fixed cost. Oh, hello again! So, back to what I was saying. The more undirected edges means the more decisions, the more calculations to be made, given the weightness properties of the graph. Now, the less amount of undirected edges means less variance of the fixed cost itself. Therefore, the easier it is for the graph to be solved.
So yeah, let's talk about the problems that are related to stacker crane. Basically, any tour problems where the minimum cost is the goal are kind of similar or related to, for example, the traveling salesman problem. It's very similar to the stacker crane problem that we are doing, except that the traveling salesman problem are visiting each vertice, and the stacker crane problem is visiting each direct edges. Also, like stacker crane problem and traveling salesman problem they're all real-world applicable problems, especially in the case of transporting of goods. And then another problem that is usually been talking like together with stacker crane problem is the Steiner tree problem, where Steiner tree problem is like a subgraph of stacker crane problem. It's looking for a subtree of graph that connects all the vertices in the lowest cost. The main difference between Steiner tree problem and stacker crane problems is that the stacker crane problem deals with a set of edges that we have visited, while the Steiner tree problems deals with a set of vertices that must be in the subtree.
Oh, hey there! Let's talk about why the stacker crane problem is important. Well, it can be used to design processes to conserve resources. Take a warehouse floor, for example. Machine movement, constrained by programming, is analogous to directed edges. Human movement, changing according to one's wishes, is analogous to undirected edges. Each movement has the weight of using up resources. Power for machines, energy for humans, and time for both. The designer wants to make a process so that it uses as little resources as possible, and in this case, uses all the machines at least once. The designer could use a stacker crane problem to help. Other examples include driving a delivery truck, operating a crane or forklift, running a service that picks up food from restaurants and delivers it to patrons, collecting and delivering supplies after a natural disaster, when some roads may be more stable and thus preferred than others. And finally, as a few academic papers have explored, a two-dimensional version of the stacker crane problem used for a telescoping robot arm that moves objects back and forth on a table, or automating chip placement on circuit boards. Solving problems like these is what makes stacker crane interesting and important.
It takes a lot to make a stew.
A pinch of salt and laughter too.
Oh, hey there!
Kids to add the spice.
A dash of love to make
Oh,
it
hey there.
nice. And you've got
Too many cooks.
too many
Oh, hey there!
Too many cooks. Too many cooks. Too many cooks.